Good day, everybody. Um, this talk is about exponential topological indices, um, their optimal inequalities and application. This is John Ward with the professor Walter Caballosa, Jose Manuel Rodriguez, and Jose Maria Cigarreta from Florida International University, Universidad Carlos III de Madrid, and Universidad Autónoma de Guerrero, respectively. Let me show my presentation in full screen. My plan is present to you some short introduction about topological indices, and then show our main result about inequalities on exponential topological indices, and some numerical experiments associated to those indices, and finally show some list about some reference used in this presentation. Well, a topological index is a single number that represents a chemical structure in graph theoretical terms via the molecular graph, and that correlates with a molecular property. It is used to understand physical-chemical properties of the chemical compounds. Topical indices are interesting since they capture some of properties of molecule in a single number. Hundreds of topological indices have been introduced and studied, starting with the seminal work by Professor Harold Wiener, in which he used the sum of all shortest path distance of a molecular graph for modeling physical properties of alkanes. Only about 1,000 benzoyl hydrocarbon are now. The number of possible benzoyl hydrocarbon is huge. Therefore, the modeling of the physical-chemical properties is very important in order to predict properties of currently unknown species. Molecular descriptors are a particular class of topological graph in indices associated to any graph modeling some molecular structure. From these indices, it is possible to analyze mathematical values and further investigate some physical-chemical properties of a molecule. Therefore, they provide efficient method in avoiding expensive and time-consuming laboratory experiments. Why were these new indices introduced? The main reason was to get a more accurate prediction of some properties of molecules than those obtained by already present indices. Topological indices based on n vertex degree of age can be used over 40 years. The best known of such descriptor is the rounded connectivity index given by the expression RGR, like shown in this slide. Two of the main successors of the rounded index are the first and second Segriv indices denoted by M1 and M2 respectively, and introduced by Goodman and Tristan in 1972. Another remarkable topological descriptor are the Pratt index P and the atom bound connectivity index ABC and the zone connectivity index Xi, defined for the three expressions appearing in this slide. Some topological indices have motivated two researchers to obtain new indices by generalizing some of the previous one. For instance, the generalized second degree M2 alpha, the general zoom connectivity index G sub alpha, and the generalized atom bound connectivity index defined by the last expression in this slide. Notice that in each case, these new indices depend on a new parameter alpha belong to R. Given a non-oriented finite simple graph without isolated vertices, we can consider, like is usual, the neighborhood of a vertex, a particular vertex of this graph. The maximum, minimum degree, and the cardinality of the set of the vertices and edge of the G, denoted by this expression in each case, and given a symmetrical function f defined on this set, we can consider the general topological indices f, capital F, given by this expression, and E capital F of the graph, given by this expression involving the exponential function. In this case, the general topological indices with these four are called exponential indices for obvious reason. Okay. Our first result is simple but powerful result. In this theorem, we show that in the case of the function f satisfies these chains of inequality for every x and y belong to this interval, then our exponential index satisfies these chains of inequalities and this inequality. This result seems simple, but in its proof, we use a powerful mathematical inequality, the Jensen inequality. Okay. Another result we can obtain are associated with the inequality 3 and inequality 4. Let me a second in order to share with you again our presentation, my presentation, because I have a little problem with the application for record this presentation. Okay. I see I see the slide again. I can continue record this presentation. Good. I'm going to complete screen mode. And we obtain also another result associated with the ABC alpha index in this case. The theorem 4 shows another inequality associated to ABC alpha index of the graph. In this case, we need the theorem 2. In fact, this result is direct consequences of the theory 2. And as a corollary of this theory, we obtain this inequality in the case of the ABC index. And this inequality improves another recent inequality associated also to the same ABC index. Good. Figure 1 shows you the absolute value of the correlation coefficient R as function of alpha for difference exponential indices. Okay. Will figure 2 shows you the correlation for different indices and several values of the parameter alpha. This illustrative example shows you the possibility to use exponential indices as a tool for QSPR or QSAR research. Finally, I want to show you a short list of reference uses to this presentation. I finish. Thank you, everybody, for your attention to this presentation.